Welcome all. In the last lecture, we derived an expression for the output power at the axle and the power consumed by the electric motor, which was here PW is the power at the axles and PE is the power consumed by the electric motor. Today, we will look to derive an expression for energy output. Specific energy output, specific energy consumption, we all know that energy is defined as the power consumed in a given interval of time. So E will be equal to P into T, where P is the power and T is the time interval. If I substitute the formula for P over here, it will be FW times Vm into T, considering the time is given in hours, so I don't need to convert this into seconds. Now I have the formula for energy, which is equal to Fw times Vm times T. I can further solve this because Vm into T will be nothing but D. So I will get E is equal to Fw times D. D is the distance over here. So the energy output is equal to the tractive force times the distance, and its unit will be watts hour. So it will be watt hour. Now I should define specific energy output. It is the energy output of the driving wheel but expressed in kilowatt hour per ton kilometer. Over here we have the energy which is in watt hour, but the specific energy output is expressed in kilowatt hour per ton per kilometer. That is the energy produced by the locomotive to travel a distance of 1 kilometer having a weight of 1 ton. So specific energy output ESPC will be equal to energy output divided by dead weight into distance between the two stations. We have the formula for energy output. We need to divide this with the dead weight and the distance between the two stations. Actually, the specific energy output is calculated to compare between the two trains. After having the knowledge of specific energy output, we can very easily calculate the specific energy consumption. The specific energy consumption of an electric locomotive will be equal to the specific energy output divided by the efficiency. In electric traction motors, we have efficiency as eta G times eta M, where eta M is the efficiency of motor and eta G is the efficiency of gear transmission. So in order to calculate specific energy consumption, we need to calculate specific energy output, and to calculate specific energy output we need to calculate the total energy output of the locomotive. The energy produced in a locomotive is consumed in accelerating the train, in overcoming the gradient, and in overcoming the mechanical resistance. So to calculate the total energy output, we need to calculate the energy required to accelerate the train, energy required while overcoming the gradient, energy required while overcoming the resistance. So let us calculate them one by one. So let us calculate the energy required to accelerate the train. Here EA is the energy required to accelerate the train, and this will be equal to the force required to accelerate the train times the distance traveled while accelerating. Distance traveled in accelerating period We need to calculate this distance using the speed time curve of the electric locomotive. This is the trapezoidal approximation of a speed time curve, and this is the accelerating period. To find out the distance traveled in the accelerating period, we need to find out the area of this triangle, and the area of this triangle will be half times the acceleration, that is the height. This will be the speed. This will be the speed, and say the maximum speed is Vm, and say the time taken is T1. So substituting this distance in this, I will get, we already have an expression for Fa, which is 277.8 WE alpha, where alpha is the acceleration, times distance traveled in accelerating period, and it is 1/2 times Vm times T1. The thing to be noticed here, that in a speed time curve, T is mentioned in seconds and Vm is mentioned in kilometer per hour. So to multiply them, we need to convert them into the same units. That is, I need to convert them into meter per second. So I will multiply it with 1000 and divide it with 3600 to convert this into meter per second. That is, I need to multiply 1000 here and divide it with 3600. We also know, if alpha is the acceleration mentioned in kilometer per hour per second and Vm to be the maximum speed during the accelerating period, then T1 can also be defined as Vm divided by alpha, and this will be in seconds. So I can substitute this T1 in this expression with Vm by alpha. I will get 277.8 We alpha times Vm by 2 times Vm by alpha, where Vm by alpha is after substitution the value of T1 into 1000 by 3600. And the unit of this EA will be in watt, second or joules, because all the units are mentioned in SI units. Further solving the expression, I will get 38583 times We times Vm square. Now this is in watt second. If I need to further convert it into watt hour, I need to divide this expression further by 3600. So 38583 further divided by 3600 into We into Vm square, I will get this in watt hour. We are converting this in watt hour because as per the definition of specific energy output, it was watt hour divided by kilometer ton. So that is why we are converting this watt second into watt hour. So the final expression will look something like this: 0.01072 We times Vm square watt hour. This is the final expression for the energy required to accelerate the train. In the same way, we will try to calculate the energy required to overcome the gradient and the resistive forces. Now let us calculate the energy required to overcome the gradient, and say the energy required to overcome the gradient is Eg, and this will be equal to Fg times distance traveled during the gradient, I should rather write in the free run period, because we generally consider the train is under the effect of resistive forces and gradient in the free run period only. Free run period. And let me consider this distance is d dash. So this will be equal to Fg times distance traveled in free run, and it is, let me consider it to be d dash. So Fg d dash. Now we know Fg is equal to 98 Wg times d dash is mentioned in kilometers, so converting into meters, it will be d dash times 1000 meters. This is d dash. So this Eg will be equal to 98 Wg d dash into 1000, and the units will be in watt second, but we need the unit of Eg to be in watt hour, so we need to divide the expression by 3600. Let us do so. It will be 98,000 divided by 3600 Wg d dash, where W is the dead weight, G is the gradient, and d dash is the distance traveled in the free run period. This is Eg, and further solving it, I will get 27.25 Wg d dash watt hour. Similarly, we will calculate now the energy required to overcome the resistance, and this will be equal to Er equal to the force required to overcome the resistive forces times the distance traveled in the resistive period, and we have considered the resistance period to be only in the free running period, so we will write d dash here. This will be equal to W into R into d dash, but over here d dash is mentioned in kilometers, so we need to write it in meters. This will be equal to 1000 times WR d dash, and the units of this will be in watt second, but we need the unit to be in watt hour, so I will divide this expression with 3600, and finally I will get Er to be equal to 1000 divided by 3600 WR d dash, and this will come out to be 0.2778 WR d dash in watt hour. Now the total energy output EW will be equal to EA, the energy required to accelerate the train, plus EG, the energy required to overcome the gradient effect, plus ER, the energy required to overcome the resistive forces. We will substitute these expressions over here. This is 0.01072 WeVm square plus 27.25 Wg d dash, which is the energy required to overcome the gradient. This is the energy required to overcome the resistive forces, and this one is the energy required to overcome the acceleration. So this is the total energy output at the axle. Total energy output at axle or wheel. Now, when we have the expression for total energy output, we can easily calculate the specific energy output, which was specific energy output was equal to energy output divided by dead weight into distance traveled between the two stations. Distance between the two stations. So the specific energy output will be equal to the total energy at the output divided by the dead weight of the train times the distance between the two stations. The distance distance traveled during this interval was d, where d dash is the distance traveled during the free running period, and d is the total distance traveled between the two stations A and B. Now, when we have the specific energy output, we can very easily calculate the specific energy consumption, and this will be equal to specific energy output divided by efficiency of the motor times the efficiency of the gear transmission. Let us substitute the expressions for these. We get we get this expression where this eta is the product of these two efficiencies, the product of motor efficiency and gear efficiency. From the above expression, we can conclude that the specific energy consumption depends upon the maximum speed between attained between the two stations, distance between the two stations, and the resistance. Resistance is generally dependent on the track configuration, the type of train I mean by the goods train or the passenger train, because the goods train do not have the windows, so the resistive force will be more on passenger trains. Hence we can conclude that it depends upon the acceleration, retardation, distance between the two stops, maximum speed, type of train, and track configuration. That's it for this lecture.